Yeah.
I was working on the cell right here. I was working on this cell and this definition for some reason, like the font isn't correct, so I know something.
You have to change it to code. So right here, select the drop down, change to code. Yeah, that'll do it.
Okay, thank you.
All right, hello. I am on. We're ready to go. Welcome to Data 8 Lecture 23. Today we're going to be talking about percentiles and a cool, nifty new method called the Bootstrap. Some announcements. So as you know, the mid-semester feedback form is due today at 5 p.m. Please fill it out. If more than 90% of the class fills it out, we'll give everyone an extra credit point on their midterm score. But only if 90% of you guys fill it out. Okay, so if you haven't done so, do it now. The midterm scores will be released after that feedback form closes, or once we get 90% response rate, whichever comes first. And we'll be allowing regrade requests as after the midterm is released. So we'll release the midterm, allow regrade requests for a day or so, and then that'll be it for the midterm. Project 2 has been released. The checkpoint is due Friday. So you'll want to go into your project 2, scroll down until you find a checkpoint mark, and then gauge from there how long you think the project will take you to get to a checkpoint so you can space yourself out effectively. The checkpoint is due Friday, and the rest of the project is due on Tuesday. So the whole thing is due on Tuesday, checkpoint due on Friday. This is a reminder that we have tutoring available this week. This week's topics are particularly particularly fun and interesting. So if you would like to go to tutoring to get more review on those topics, I suggest you sign up because they can get pretty nuanced and subtle. Any questions? All right. So basically, in this point in the course, we are halfway done. What we've done is we spent the first part of the class covering tables and Python and manipulation of data. And then we spent a bunch of time talking about statistics, so sampling methods, hypothesis testing. What we're going to do this week is complete out our inference part of the course. So we're going to be talking this week about confidence intervals and their relation to hypothesis tests. And then we're going to move on from there into prediction, so talking about regression and machine learning. Okay, so that's kind of where we are in the big roadmap of this class. So today I'm going to be talking about I'm going to spend some time talking about another statistic that is useful to us called a percentile. And then we're going to talk about the Bootstrap, which is another sampling method. Cool. So percentiles. Percentiles are a useful statistic because sometimes you want to know, OK, in a set of numbers, which number is bigger than most of the other numbers? Okay. For example, we've seen it in the case of the median, where we said, OK, the median is kind of like that middle number in the set. Turns out to be pretty useful for describing where most of the set is centered around, right? So our definition for percentiles in this class is if we're looking for the 80th percentile in a set of numbers, we're looking for the number that is at least as large as 80% of the elements in the set, which means that if we have this list right here with these 5 numbers, okay, so we have 1, 7, 3, 9, 5, the 80th percentile is 7, because 7 is a number that is at least as large as 4 out of 5 elements in my set. Okay. Another way of computing it is the 80th percentile is what we do is we take 80 divided by 100 to get 4 out of 5, and then we multiply by the number of elements in my set, 5, to get, we're looking for element number 4. Then we look, OK, 1, 2, 3, 4. I'm looking for element number 7. So the 80th percentile is element number 7. We can ask for any other percentile that we want, going from 0 to 100. Okay, so percentile, size of my set. If we ask instead for, say, the 81st percentile of my set, the 81st percentile of my set does not correspond to any particular one element. So what we do is we compute that, and we take the next greater element. So the 81st percentile will be element 9. Okay. But the 80th percentile will be 7. That's because, according to our definition, the number 9 is the only number that is in this set that is at least as large as 81% of my elements. 7 is only as big as 80% of my elements. Okay. So we have this percentile thing. It turned out that the median is the 50th percentile of my set. So you've already seen percentiles in that sense. But we're going to be looking at different percentiles because we're going to be looking at, in my set, like which numbers are kind of in the middle part of my set. Okay, so that's why I introduced it now. There is a function for doing that. If you look at the percentile function, if we've imported data science, this function is already available. What you can do is you can say percentile p, which is a number between 0 and 100 for your percentile, and put in values as a second argument here, which could be an array or a list. It'll just return to you the pth percentile. So if you pass in 80 and pass in that list that we had before, it'll return to you 7. Okay. So here's a question for you. Which of these expressions evaluates to true if my set is these 5 numbers, as we've just seen? Okay. So is this true? Is that true? Is that true? Is that true? Talk it over with your neighbor. Okay, so how many of you guys think the first one is true? Is the first one true? Any takers? All right, how about the second one? Second one true? What about the third one? Is the third one true? The fourth one, is the fourth one true? Not bad. Okay, let's check it out. So I have here a notebook, and I'm going to run that. So here is my 5 numbers. And I'm just going to make a table with all the percentiles that I've asked for in this question. I run that. Here we go. So we see the 40th percentile of my set is 3, and the 39th is also 3. The 10th percentile of my set is 1. So okay, let's go back to the questions. So percentile 10 is 0. That's not true. Okay. So as a general rule, one convenient thing about the way we've defined percentiles in this class is that the percentile of a set will always be a number in the set. It will never be something that's 0. It won't be like 100 if 100 is not in the set. It will always be a number that's contained in my original 5. Okay, so you should remember that because of the way that we've defined this percentile thing. Okay, so the 10th percentile is 1 and not 0. So this one is false. Percentile 39 equal to percentile 40. 9 and 40 are both 3, so that's true. So remember that we round up to the next greatest numbers. So if we have, so once we order so what we want to do is we want to take that list and we want to order it. Okay, so we want to take the numbers in my list. So let's say 1, 3, 5, 7, and 9. So we want to order them first, and then we can give them percents. So we can say, okay, divide a list into 5 parts. So here we have like 20. Let me delete one space. 20. Here it's 40. Here is 60. here's 80, and here's 100. Okay. And what we can do is we can say, okay, if we ask for the 40th percentile of this list, the 40th percentile is 3, so I'm done here. If I get something that's in between 20 and 40, then that goes up to 3. If I get something that's between 60 and 80, that goes up to 7. Well, another way of thinking about this percentile thing. Okay. So in this case, 39 and 40 is both 3. But 40 and 41, so 40 is 3, but once we go up to 41, now we're looking at the number 5. So 5 is the 41st percentile of my list. Finally, the 50th percentile of my list is indeed 5, because that appeared in between 40 and 60. So we go up to the next number, that's 5. Any questions about that? Cool. All right, so we're going to be talking about estimation today. And what I want to do first is briefly recap the stuff that we've already covered in this class, and then we can move on to more interesting things. Okay? So I want to get it fresh in your head, and then we can do something more interesting. Basically, in estimation, we want to ask the question, how big is an unknown parameter? So for example, when we're looking at the warplanes, and we're trying to figure out how many warplanes there are, our question was, how many warplanes are there? Right? And there are two ways of answering this question, depending on how lucky we are. So if we're lucky enough to just have the whole population, so let's say we had all the warplanes that Germany had, and there are 1,000 of them, we can just say, OK, if there's 1,000, I'm done here. So if we had the whole population, we don't need to do anything special. We don't need to do any probability, any statistics, any of that stuff. We just calculate it, and we're good to go. Unfortunately, life is hard, and oftentimes we don't have a census or a population of like everything that's out there. Instead, we only have a sample. Okay? So if we only have a sample, we still want to be able to say, OK, this sample is better than having no sample. I can use that sample to tell me something about the population. And inference, the idea of statistical inference is being able to take that sample and draw some conclusions about the population, even though you can't see the population. Okay? So the idea is take a sample, and then compute the statistic on the sample, and use the sample to estimate something of interest in the population. That's the idea. Let me show you an example. OK, so I have this table. This table contains, if I run that, this table contains all the public service employees in San Francisco. Wow. And what I've done here is I've categorized them according to their organization group. So this particular employee worked in public works, transportation, and commerce. And then I have here the actual job that this person had. So this guy was water quality tech 1/2. And I've included also the total compensation of that worker. So it's salary plus benefits added together. That's what goes in this column here. So this guy made $117,000 last year, which is pretty nice. Okay, I have basically left this table as it is. I have cut out the people that made $10,000 or less, because there were a bunch of contract workers or part-time workers in this original data set. I'm only interested in looking at full-time workers for the most part. So I've cut out that bottom 10,000. But otherwise, this contains all the other San Francisco employees. Okay, so we can take a look at this data. So let's sort. I can sort this data. Sort by column number 0, 1, 2. And if I run that, I see that the bottom end of my compensations are people here. So human welfare, neighborhood development, community health. I guess these are positions that you don't want to take if you want to make more than $10,000. I can also sort in the opposite order. So let's see what makes the most money. Setting equals true. And bam, wow. So that chief investment officer of San Francisco made $648,000 last year. What a scandal. So I have here the people that made the most money. We can see people that made money in between, say, like $10,000 and like $700,000-ish. Okay. So what I'm going to do is let's plot them on a histogram to see the distribution of salaries. So I'm going to make that smaller. Show 3. There we go. And plot that. So I can take sf.hist, and I want to hist column number 2. OK. It looks like this. Maybe I want more detail. Let me put in some bins. So let me call this comp bins, and just put in some bins here. So we said salaries generally go from like 0 to 700,000. And let's increment by 25,000. Okay, so let's set my bin equal to comp bins. And then we might as well make the units nice while we're at it. So unit equals dollar. All right. This is what we get. So we can see here that we had some people that made like between 0 and say $60,000 a year. And then we had a bunch of people that made around like $100,000. And then it kind of tails off at the end here. And then over here is like the chief investment officer of San Francisco. Okay, so he's making way more than everyone else. Cool. So this is my entire population of, I'm going to call it the entire population of full-time workers, public service workers in San Francisco. They're required to release this data because of some Open Data Act, so we have access to everyone, all their salaries. But let's suppose I did not have access to everyone. So let's suppose that we only have access to this sample. I'm going to call it sample from population. And I'm going to say, let's suppose that we only have a sample of 200 of these workers. So I'm going to say with replacement is false. So we get 200 unique workers. I'm going to show you what that looks like. Here we go. So we only have these 200 guys, 200 people working. Okay. What is the median of my population in terms of what is my median compensation in my population? Let's suppose I didn't know. And in fact, you don't know because I haven't shown it to you. So there is a median compensation in this distribution here. But we don't know what it is. Let's take our sample and see if our sample gives us an estimation of our median. So here's np.median. Take my sample and take the column of salaries, compensation, column number 2. And here we see, OK, my sample says the median salary is $108,000. Cool, so we're done. We're not done. You look at this and you're like, seems kind of suspicious, right? Do I know that this is the population median? Like, do I know this number is accurate? I don't, right? Because in the back of your mind, you're like, well, that sample was pretty random. So if I had actually run that, if I ran this again, so let me just show 3 to make it smaller. If I run this again and I run this again, I would have gone a different median, right? Different median. So which of these medians is actually good? We don't know. But we can try to answer that question. So if we have one sample, we can only compute one estimate, right? So if I had gone out and taken 200, if I had gone out and interviewed, say, 200 employees, and that was my sample, I can find the median salary in my one sample. And that's about it. I can only get that one median. But I do know in the back of my mind that if I had chosen another random 200 people to interview, I would have gotten a different median compensation. Okay? So the question is, how different could my estimate have been, right? So is my sampling procedure likely to give me something that's close to the population median or not? For example, let me go back to my demo here. We got about 100,000 as my median compensation, right? If I go back and take another sample, let's suppose I go back and take a bunch of samples. I notice that my sample medians all come within the range like 100,000, 101,000, 102,000. If they all come in that narrow range there, I can pretty much say, OK, the population median is probably somewhere in that range. On the other hand, if I go back and sample, and suppose I do a really bad sampling and I sample homeless people on the street, and their average salary is like, say, $10. So I get $10 in one sample, and $1,000 in another sample, and then $150,000 in another sample. Now I have a lot of variation, right? And so the question I'm trying to answer is, how different can my estimate have been? Because that gives me a sense of how accurate my sample can give me, right? How accurate an estimate a sample can give me. Okay, so let's try that. So the question is, OK, I get this median, but what is a range of these medians? Like, can I get a median that's really low? Can I get a median that's really high? Like, how accurate is my sampling procedure? Let's try to answer that. I'm going to make a brief aside and talk about appending to lists. Okay. This is just a shortcut that I'm going to use for this lecture just to save some typing. It's not super important, but I just want to show you what it is so you get a sense of what I'm doing. Okay. So before, we've seen that if an array, make array, let's say like 1, 2, 3, 4. So here's A. I can use np.append to add a number to that array. So if I append 5, I now have 2, 3, 4, 5. Okay. And I also know that A is left unchanged by this np.append. There's also an append that works on lists. Okay, so if I have a list, A equals a list, let's call it B. B equals a list 2, 3, 4. Here's B. So this is a list, it's not an array. Lists also have an append method, so I can just call it b.append. And the way it works is it doesn't create a new list, it just changes my original list. So now B is changed. Okay. So that's the only difference. It just saves me some typing because I don't have to type np.append and then save that to a new variable. I can just do b.append and just be done with that. So if you see me do like something .append something else, and it's a list, just know that this is what's happening. This append method is different than the numpy append method. Okay. But otherwise, those two are the same thing. So if this is confusing to you, all you have to do is just use an array and just stick with np.append with an array. I'm just going to use this for today just to show you a different way of doing it and also to save some typing. Okay, so that's it. Cool. So back to our original question. Is this median accurate? Or more precisely, if I take more samples from a population, what is a range of medians that I can expect? Let's try it out. So what I'm going to do is take a sample. Take the sample. Okay. Here's a new sample. I'm going to compute its median. Just copy and paste that code. So I run this. I get a new median, right? New medians, new medians, new medians. And I want to just put that in a loop so I can see the variation of those medians. So let's call that. Let's say I want to do that 100 times. Percentage equals 100. For I in np.a range repetitions. Bam. I'm going to make a medians list. And then just say medians.append that guy. And now I have a list of my medians. So run that. And there we go. Okay, so I have 100 medians based on 100 samples from a population. What I can do now is put that into a table, and I can show you what those look like on a scatter plot. So make a table. Table.with columns. Let's say the first column is just like the number, like the sample number that I have. So let's make that an array of, let's say, 100. Okay, because I have 100 samples. And then here is my median. Median. Put my medians in there. Medians. Okay. I have this table. In my first sample, I got a median of 107,000. Here I have 107,000. Here's 101. Let's plot that. Scatter plots and put the I column on the x-axis. Here we go. So what do I notice in a scatter plot? Talk to your neighbor about it.
But it's not much denser though.
Okay, so what do we notice? We notice here, so each dot here is one sample that I've taken from a population. Okay, and the position of that dot on the y-axis is the median compensation in that one sample. So I have here 100 samples, and I see here that most of my samples fall in this range, like fall around here, right? Around 107,000. Most of them come within, say, like 120. Most of them fall within like 120 to 95,000. So I can say that my population median compensation is probably in this range, 95,000 to 120,000. Okay, so I can say, okay, it's probably somewhere in this cloud of points here. Okay. So are we done now? Unfortunately not, because I cheated in my sampling, right? So in the real world, I don't actually get to go back to the population and draw new samples, right? So in the case of the German warplanes, I kind of saw some like questionable looks on your guys' faces when I talked about like, taking more samples. And I don't know whether you're actually thinking of this, but in this case, if we're looking at the warplanes, if you observe 100 warplanes, that's pretty much all we have to work with, right? It's kind of hard for us to go back and take another 100 warplanes and then go back and take another 100 warplanes and then look at the distribution of that as we've done here, right? So take a look at how much extra work I did to get this. I went from 1 sample to 100 samples. Each sample was 200. So I looked at like 20,000 people, right? That's a lot more than what I originally did. That's a lot of extra work. And unfortunately, in the real world, you run out of either time or money or both. Okay? So you can't do this in the real world. You can't actually go back to your population and get a new sample. So with 1 sample, you can get 1 estimate. If we take more samples, we can get more estimations of my value. But unfortunately, okay. So what do we do? I wonder. You can wonder too while we take attendance. Okay, open that up. I'm going to switch back to the link. So open, Sesame, okay, go. Okay, you can go ahead and keep filling it out. I'm going to talk now about a method that we use to deal with the fact that we only have 1 sample and we can't get more samples. Okay, so over the course of the last couple of weeks, I've been like slowly pulling the rug out from under you, right? So we started out with the warplanes example, and we said, okay, we happen to know that there are 300 warplanes. So if we know that there are 300, we can take multiple samples and see how that goes. That's not really realistic because we happen to know in the beginning that there are 300 warplanes, right? So I kind of cheated there. We happen to know the population parameter before we did any sampling. Okay, so first we had the population, and then I said, okay, suppose we did not know the population. So I took out that I took that away from you guys. We don't know the population anymore. We can only take samples. Okay, so we said, okay, if we didn't know that there were 300 warplanes, and we took a bunch of samples, I can still figure out, okay, there's probably 300 warplanes. Now I'm taking out the ability to take more samples. Okay, so before we said, in this case that I just showed you, I said, okay, we can go back to the population and get more samples. I still don't know what the population median is, but I can go back and get another sample. I can get another sample. I can get 100 new samples and use that as my estimation. So now I'm saying, okay, I'm taking that away. You don't get more samples. You only get your 1 sample. So what do? So the technique that we use is called the bootstrap. Okay, and it comes from kind of this antiquated turn of phrase where it's like if you have boots with straps, which no one does anymore, but if you had boots with straps, you could try to like hop over things by pulling on your own straps and like hopping over. And it turns out that it doesn't often work that well if you actually try it out. But in this case, this technique actually does work. So all that is to say, it's a cool name it's a random name for a technique that's pretty cool. Okay, so basically what we're going to do is say, okay, we only have 1 sample. We can't go back and get more samples. What do? What we can do instead is note that our original sample, if it's both large and randomly drawn from the population, will probably look like the population. Okay, so we assume that our sample probably looks like my population if it's large and random. Okay, then we can just sample from our original sample. So I see the skepticism. The idea is, So here the idea is, if you have a population, and we have a sample from the population, but we only have one sample, what we can do is we can say, OK, I'll pretend that my sample is the population. And then what I'm going to do is sample with replacement from my one sample to get more samples. Okay? And the reason why I can do that is because my sample, if it's large and random, appears like the population. So you see this sample here looks mostly like this population here. So what I'm going to do is say, OK, I don't have the population. I don't have multiple samples. But I'm going to pretend that my sample is a population and take multiple samples from there. Okay. Now, seems questionable, but I'm going to show you that it works. So first, some rules. So what we're going to do is take my original sample, draw at random with replacement. So if we draw without replacement, all we're doing is shuffling around our original rows, right? So we're not doing anything. We're not like changing. We're not getting any sense of the variation in sample median. So we want to draw at random with replacement so we can get duplicate values sometimes. As many values as my original sample contained. So if my original sample had 200 compensation, 200 workers, I want to take another sample, a resample of 200, of size 200. That gives me a measurement of the variability of my original sample of size 200. Okay? So it has to be the same so that we can compare the two estimates. Let me show you that works. Okay, so, oh, hello. How exciting. Unread messages. OK, bye. OK, so we had this, but I said you're not allowed. You're not allowed to do that. So let's try out this method called the Bootstrap. Okay. So if I have my sample from population, here it is. Okay. This guy's job is train 3. Interesting. OK, cool. So let's look at the median of my sample. And median of my sample from population. Okay. So wow. Oh, whoops. I need to take out the column. Column 2. There you go. Okay. So now I'm going to say, OK, we don't get to go back from the population. All we have is this guy. So we take this guy and we say, OK, what is the median of my sample? In this case, it was 120,000. Now I'm going to sample from my sample. Take my sample and call .sample on it. Now remember the defaults of the sample method. By default, it'll take out a sample the same size as my original with replacement. It's almost as if we expected you to do this. So if I call .sample on this method, on this table here, I'm going to get a sample of size 200 with replacement for our original. That is a criteria, or that is a kind of sample that we want for a Bootstrap method. Okay, so take out a new sample of size 200. And we see here we have a new sample. I can ask, so let's call this a resample. Because I'm like sampling from my sample, it's a resample. Here's a resample. And I can ask, what is the median compensation of this new sample that I have? Resample dot column 2. Now we had 112,000. Okay. If I were to run that again, bam, 113,000, 124,000. Okay. So in this way, I can get a sense of the variability of my estimation, right? Before I had one sample, I had one number. I don't know how good that number is. I don't know like how much that number can vary if I had more samples. When I do the Bootstrap, now with just my one sample, I can get a sense of the variability of my sample. Sorry. So run that a couple of times just to convince you. Yeah. So 117,000. This is Bootstrap. Okay. So now you're wondering, OK, what can I do? What happens if I draw these medians on a histogram? So that's not too hard. Copy and paste that code. Copy and paste that code. And put that in a for loop. So here, oops, for I in np.a range. Let's say 1,000 repetitions. OK, do that. I'm going to save those medians in a list. So resampled medians equals a list. And I'm just going to take my resampled medians and append to it. So call this the median and append that median. Yeah. Okay. I run that, and let's see what we get. Okay. So now I have 1,000 estimations of the median compensation. Let's put that into a table and put them on a histogram. So table with column. Let's call it resample median. And put this guy into that column. There we go. So here I have the table, and I can draw a histogram. So let's draw it. Hist. Okay, so here we go. So now I've taken resamples, 1,000 resamples of my original sample, taken the median of each one, and plotted them on a histogram here. Okay. Now you look at this, and you're like, okay, what does this mean? I want to ask you what that means. So look at my original SF table. Histogram column number 2. I get back this original histogram. Actually, let me get the bins and stuff right. So let me go up here, copy and paste that. There. We start off with this histogram, and now we have this histogram. So histogram here, histogram here. What is the difference between these two histograms? What am I showing here, and what am I showing here? Talk about it with your partner. Unfortunately, I can't show them both at the same screen. So I'll just scroll back and forth slowly so you can kind of see about, okay, so A and then B. Talk about it.
The second one is all about population. It's a large and random. That's not the question.
All right, so let me ask you. I have this original histogram here. What does a bar here represent? What do you guys think? So this was the distribution of compensations in my original SF table. What does this histogram showing? What does a bar represent? Can I get a volunteer? Yeah.
The proportion of people who make that amount of compensation.
Right. So each bar here says, okay, so this bar says, okay, so there are some people that made 20,000, between 20,000 and say, I believe that's 20,000 and 22,000. So right here, there's this many people who made that much money. If I go over here, there is, this is 100,000. Okay, so there are a bunch of people who made 100,000 and less people who made like $200,000 and even less people who made $300,000. So these are, so each individual person, each individual worker determines, like, once we fit them into the bins, how high the bar goes, right? So each of these represents individual people. On the other hand, I have this histogram here. What am I representing with a bar in this histogram? Right, so these are not people. These are not individual people. These are individual medians, right? Because I've taken samples, and I'm taking the median of each sample, and then plot the distribution of medians. So these are not people, these are medians. Okay? If that's confusing to you, I suggest you look back and look at the procedure that I did, and try to figure out the difference between the two. That difference is really important because if you get confused, you're going to be very confused. Okay, so I'm going to put that there. I'm going to ask you, what is the difference between these two? Question mark. Okay, so right here, sample, taking a bunch of resampled samples, taking the medians of each one, and now I have this as my resampled medians. Okay. What I can do now is say, okay, before we had the scatter plot, we noticed that most of my dots fell between the range 120,000 and 95,000. So most of the dots fell in this range. If I have this, I can also ask the same question. Where do most of these medians come in? That gives me a sense of where that population parameter might be. I can say, okay, let's take the middle portion of this and see, and use that as a measurement of how variable my estimation is. So I just conveniently have the code here. What I'm going to do is I'm going to say, okay, look at this histogram of medians and pull out the middle 95%. Okay. So right here, I looked at this scatter plot. I didn't say anything like pull out the middle 95% for anything. I just said, okay, it looks like most of the dots fall in this range. I'm just formalizing that and making it more precise and saying, okay, I have here a bunch of medians. I'm only going to take the middle 95% and say that is the range of values that I got. Okay, so look at the middle 95%, and I did that here using that percentile function that we just talked about at the beginning. So if I want the middle 95%, okay, so I want to shave off 5% from both sides, or shave off 5% total, which means I need to shave off 2.5% on the left side and 2.5% on the right side. Right? So if I want the middle 95, I have 5% that I need to shave off. So 2.5% goes on the left. The other 2.5 goes on the right. That is why I'm going to use this percentile and put 2.5 as a left endpoint and 97.5 as a right endpoint, so that the area or the proportion of values in between these two is 95%. And we see that from our estimation, 95% of our medians were between 109,000 and 131,000. Okay? So now we have kind of a range of medians, an estimation of our variability. So let me show you what that is. Okay, so here, the medians again. So this histogram is the same as what we've done before, right? Same thing. This, the same as this. And what I've drawn in yellow is that middle 95%. Okay, I'm taking the middle 95% and said, okay, plot out. And in the red is the actual population compensation. Okay. Now it looks like in this case, and I just happened to get lucky here, that this interval, this 95% middle interval here, did not contain my population median. That happened because I just got unlucky with my sample, right? So I took a sample. That sample happened to have a really high median, right? Originally, let me just go back up, had a median of 117,000. Or sorry, this is my resample. My original sample had almost 120,000 as my median compensation, which is pretty high. Pretty high when we looked at our original scatter plot, right? So it's pretty high. And because of that, my estimation of values for that median is also pretty high. It's not contained in population. But if I were to do this again, let me just take this code, take a new sample, okay, put that here. If I were to repeat this, so grab another sample, and then resample that again, so do that. So I'm resampling, taking a new sample, doing the same process over again with a new sample, and then drawing the histogram. So let me draw that. Okay. And remove that. All right. If I do that whole thing again, darn, I get nothing. If I did the whole thing again, cross my fingers, there we go. Did the whole thing again, oh, I got unlucky again. So maybe this method is not so great. Puzzling. Oh, it's because I'm not getting a new sample. You're right. Say, okay. So the problem I did here, so the reason why this didn't work or the reason why I'm not getting new estimations is because I'm taking my original sample. I'm not getting a new sample for my population. Okay, so one key thing to note is that if I take my original sample and over again, I'm basically going to get that same confidence interval here. And confidence interval is basically always going to miss my population if my sample was bad in the first place. Okay, but if I take a new sample, let me grab that all the way back. Where is it? Aha, found it. Grab that. Now I'm going to now it's like square in the middle. Excellent. Let me try it again. Oh no, I missed. Wow, I am just really unlucky. Okay, so there it is, barely in there. Try it again. So it's in there again. So how often will that interval contain my actual population median? I'll leave that as a question that we can answer tomorrow. I'll see you tomorrow.
For the resample